Welcome everyone. Today we're delving into the fascinating world of fluid dynamics, specifically focusing on the concept of viscosity. Viscosity, in simple terms, is a measure of a fluid's resistance to flow. Our experiment today will involve two common liquids, honey and vegetable oil. These substances, while familiar to us all, exhibit strikingly different behaviors when it comes to flow characteristics. So we are going to be dropping a spherical object into both of these fluids and we'll be measuring their velocities. We will also be going over how the walls of the tubes affect the velocity of the dropping object and account for it to measure the true velocity of the object in realistic scenarios.
For this experiment, we need to understand the concept of Stokes' law and Reynolds number. Stokes' law is an equation that represents the drag force resisting on small spherical particles through a fluid medium. Reynolds number is the ratio of inertia forces to viscous forces in the fluid flow. Stokes' law only applies when the velocity of the object is very low, or the sphere has a small diameter, or a combination of both is true. Stokes' law is only applicable for spherical objects, so in this experiment we'll be using marbles as the objects falling between.
Alright guys, so now we'll be going over the materials for the viscosity experiment. We use basic household items, so if you guys would like, you can run the experiment at your own time. We have honey and we have some vegetable oil. We have a ruler and we have two smart water bottles, which we filled up briefly to about 10 centimeters each, just to keep it consistent. We also have two spoons, one for each liquid, to pick up the small bead that will be dropping inside. Now we will be running the first test. Now we'll be running the second experiment.
Look at that.
So these were the results of our experiment. For the spherical object to pass through the oil, it took 2.03 seconds, while for the spherical object to pass through the honey, it took 10.97 seconds. To calculate the velocity for the object, we put the distance that it took over its time, and for the oil, we got 4.93 centimeters per second, and for the honey we got 0.91 centimeters per second. Normally, these would be the velocity values for the spherical object in an infinitely open space. However, since the spherical object was confined to the water bottle, we need to find the corrected velocity, which is equal to the original velocity found times K factor. And to get the K factor, we use this equation. And this K factor represents the drag force caused by the sides of the water bottle.
In conclusion, it can be observed that the object falls through honey much slower compared to in vegetable oil. This happens due to honey having a much higher dynamic viscosity, kinematic viscosity, and a much lower number for the Reynolds number. Here, dynamic viscosity is the resistance imposed by one layer of the fluid on another layer of the fluid, whereas kinematic viscosity is the viscosity or resistance caused by gravity or shear force or a combination of both. So honey has a Reynolds number that ranges between 50 to 100, whereas oil, including vegetable oil, has a Reynolds number that ranges between 1000 to 2000. Now, Reynolds number is proportional to flow momentum, whereas it's inversely proportional to viscosity or the flow resistance. Since honey has a low Reynolds number, we can see or finalize that for honey, Reynolds number is mostly governed by viscosity. This further explains why the falling object falls significantly slower through honey, whereas for the vegetable oil, the falling object fell almost completely instantly. Low Reynolds numbers correspond to laminar flow, whereas high Reynolds numbers correspond to turbulent flow. This is why in our previous viscosity lab experiment, whenever we dropped an object through any fluid that had a high Reynolds number, we would get a higher percentage error because the object had to go through more turbulence. Finally, from the viscosity lab earlier this semester, we found out that the percentage error would be significantly higher in viscosity calculations when the object did not follow Stokes' law. Objects that do not follow Stokes' law are shaped in a way that it is further affected by turbulence, causing more error in our calculations. Since Stokes' law only applies to spherical objects, we avoided using non-spherical objects for this project to keep the calculations as accurate as possible and get the most accurate possible measurements.
I hope now you have a better understanding of why some fluids flow slower than others, why some fluids are stickier than others, and how we can measure these factors. Thank you very much for watching. Keep learning and keep growing.